Hello, ladies and gentlemen. Today we're going to be talking about nuclear chemistry, introduction to nuclear radiation. So, we're going to talk about how nuclear reactions happen, how to predict products of them, that kind of thing. After today, you will be able to explain how an unstable nucleus releases energy, differentiate between chemical and nuclear reactions, and identify the three types of nuclear radiation and their properties. A quick review. So, things that you should already know and already be familiar with. The word isotope. Isotopes are atoms of the same element with the same atomic number, but different numbers of neutrons. So, they have a different mass number. Examples include carbon 12 and carbon 13. So, they have the same atomic number of 6, but because they have different neutrons, their mass is different. Other things you should know: the atomic number is the number of protons in a nucleus. This cannot change during chemical reactions, but it does change during nuclear reactions. Again, atomic number does not change in chemical reactions, but it does change in nuclear reactions. Mass number is the number of protons and neutrons in the nucleus of an atom. Other things you should already know and already be familiar with. This is a shorthand way of indicating mass number and atomic number for an atom. So we have the mass number on top here of carbon and the atomic number on bottom here of 6, and then C for the letter for the element carbon. Radioactivity was first observed by Marie and Pierre Curie, a husband and wife couple, and they observed it using uranium atoms. Radioactivity is the process by which substances spontaneously emit rays and particles. Unstable radioactive isotopes are called radioisotopes, are transformed into stable non-radioactive isotopes of a completely different element. Radioactive decay is the process by which an unstable nucleus emits radiation and energy in order to obtain a more stable state. Here are some uses of radiation. We have smoke detectors. They can contain americium-241, and the smoke would absorb the particles of the americium, causing the alarm to sound. It's a faster way for smoke detectors to work. Sterilizing. Gamma rays are used to sterilize hospitals and food. Radioactive dating. We have carbon-14, which is a common radioactive element inside all living tissue. It can be used to tell the time since death. And we can say that's how we know the pharaohs lived however many years ago. Three other uses for radiation. We have radioactive tracers, not the kind that they would put inside humans to track you, but they track where things are going. So we have technetium-99. It's used to detect leaking pipes and kidney malfunctions in people. Cancer treatment, radiation therapy. Gamma rays are used to destroy harmful cells. And finally, checking welds. If gamma radiation leaks through a weld, the weld is not strong enough. So we have three types of radiation that we're going to speak about. Our first is alpha, then beta, and finally gamma. Alpha radiation Due to its large mass and charge, alpha particles do not travel very far. They cannot penetrate very well. A sheet of paper or the surface of your skin stops them. However, they are toxic when ingested. They are made of 2 protons and 2 neutrons, have a charge of +2, and a mass of 4. Written as 4-2E. He, sorry, 4-2He. Here is an example of alpha decay with uranium-238. So we have uranium-238 with an atomic number of 92. It spontaneously goes through radioactive decay. So it does it on its own. Nothing has to change. And it forms a whole new element, thorium-234, and gives off this alpha particle of radiation. Things to make note of. The atomic mass went down by 4. The atomic number went down by 2. In beta radiation, it results from the breaking apart of a neutron into a proton and an electron, usually written as 0, -1e, or beta. Beta radiation has much less mass than an alpha particle and therefore can penetrate things more easily. It can pass through paper, but is stopped by foil or wood. Has a charge of -1 and a mass of about 1/2000th of a proton. Here's an example of beta decay of carbon-14. So we start with carbon-14. It spontaneously goes through radioactive decay, forms an entire new element of 714 nitrogen, and we end up with 1 beta particle as well. Things to notice. The atomic mass, the mass number, did not change at all. It was 14. It's still 14. But the atomic number went up by 1, therefore changing the entire element. Our last type of radiation is gamma radiation. Gamma radiation is a high-energy photon emitted by a radioisotope, usually written as 00, and then that sign is called gamma, or just gamma, often emitted with alpha or beta particles during radioactive decay. Has no mass or charge. It is extremely penetrating and can be very dangerous. So it goes through most things. Easily passes through wood, paper, and the human body. Penetration can be stopped, although not completely, by several centimeters of lead. So that's why when you go to the dentist, they put on that lead apron over the top of you so that none of the radiation leaks on you. Here is an example of gamma and alpha emission from thorium-230. So we start off with thorium-230. It spontaneously goes through radioactive decay, forming an entire new element. The reason there's a new element is because we're giving off an alpha particle. We're also giving off this gamma particle. The gamma particle does not change anything, but the alpha particle does. Okay, we're going to go through some practice here. I'm going to talk through one, and then you should pause the video and try to do the other 2 on your own. So our first one is alpha emission, and we have radium-226 giving off an alpha particle and changing into radon-222. So I have radium-226. Ra is the symbol for radium. Its mass, 226. When I look at a periodic table, radium is element number 85. So just from that, my mass number is 226. My atomic number is 85. It's giving off an alpha particle. Go back to your notes earlier and find out an alpha particle, what it looks like, how we write it. You're going to write it 4, 2, He. So it has a mass of 4 and an atomic number of 2. Because it has those things, we change the starting element into a completely different element. We're going to take our mass, subtract 4. Our new mass is going to be 222. Take our starting atomic number, subtract 2. We're going to end up with 83. So now to do some practice, we're going to do some alpha, some beta, and some gamma practice. Our first one is alpha. So we're going to start with radium-226. The mass number is 226. And radium's atomic number is 88. So I'm going to go ahead and write that up here. Next, I have my alpha particle. If you go back to the notes, you'll find out that an alpha particle is written as 4,2He, which means it has a mass of 4 and an atomic number of 2. So radium is giving those off. So we're going to start with a mass number of 226, subtract 4. Our new product has a mass number of 222. If we start with an atomic number of 88, we're giving off 2 of our protons. So our new element has an atomic number of 86. So for radon, we have a mass of 222, an atomic number of 86, and the element symbol is Rn. Here's some more practice. See if you can do these on your own. And then come back and listen to the answers. So first we have 21884 polonium. Polonium is going to decay with an alpha particle, and we're going to end up with another particle. So our 218, we're going to lose 4 from the mass. So 218 minus 4 is 214. From our atomic number, we have 84. We're going to lose 2, so that's 82. And looking at the periodic table, if we go from 84 to 82, 82 is lead. So we're going to write Pb. On our next one, we have the products, and we're going to what we started with. So 221 plus 4 is equal to 225. And our atomic number is going to be 87 plus 2, so 89. Looking up what number element that is, or what element it is from the number, it's actinium. Okay, so that's alpha decay. During beta emission, we're giving off a beta particle. Okay, so we're going to start with uranium-239. Mass number is 239. My atomic number, 92. go ahead and write the nuclear symbol up here. Then we have our beta particle. If you look back in your notes, a beta particle is written as 0, -1, E. So we're gaining an electron. Our mass would be 0. We're going to gain 1 electron. So I write a -1 there because electrons are negative. And then I'm going to figure out my other product. So since I didn't change my mass is going to stay the same at 239. But because I am changing my atomic number, I'm going to add 1 to the atomic number. So my nuclear notation for my answer is 239, 93 Np for neptunium. Okay. Two more practices. You might want to pause the video right now, see if you can do them on your own. So we have thorium-228 going through beta decay. So nothing's going to happen to our mass number, so that's still going to be 228. But our atomic number is going to go up by 1. Element number 91 is protactinium, Pa. On the opposite, for letter B, we have the products. We're going to our reactant. So we have 94. We're going to subtract 1 for our atomic number, and our mass number is going to stay the same. Then we figure out what element that is, and it is neptunium. Okay. Final type of radiation, gamma radiation. We're going to start with barium-137. Barium's atomic number is 56. Its mass number 137 because it told us. We're going to emit a gamma ray, which is often written like an upside down, a very fancy V. Okay. It has no mass number and no atomic number, so therefore nothing changes. We're still left with 137 as our mass and 56 as our atomic number. Here's one practice for gamma. Write the balanced nuclear decay equation. So our atomic number stays the same, our mass number stays the same, and our element stays the same. We're going to do our last little bit of practice here. So for these, I want you to tell me what the question mark would be and then what kind of radiation it is. So for the first one, we start with sulfur. It has 35 for its mass number and 16 for its atomic number. Notice the mass number does not change. The atomic number increases by 1. What kind of radiation is that? If you said beta, you are correct. What goes in the question mark? Our beta particle 0, -1 E. For our second example, we have 210 polonium plus or yielding a question mark, something we don't know, plus 42He. That 42He is what tells us what kind of radiation it is. This is alpha radiation. What should be here? We're going to subtract 2 from our atomic number, so that's 80. We're going to subtract 4 from our mass number. Okay? What element is number 80? Mercury. Oh, it would help if we did math correctly. Sorry, guys. Okay, so we're going to go through these last bit of practices. We have 3516 sulfur going to 3517 chlorine. The atomic mass, the mass number stays the same, but the atomic number goes down by 1. So that has to be beta radiation, and our question mark should be our beta particle. For the next one, we have 21084 polonium yielding our question mark plus 42 helium. The 42 helium tells us this is alpha radiation. What goes in the question mark? We're going to decrease our mass by 4, so 206. We're going to decrease our number by 2, 82. 82 tells us that this is lead. And we are done with that. Next, we have xenon 131 with an atomic number of 54. In our products, we have xenon 131 with an atomic number of 54. That means this is gamma radiation. And our question mark should be our crazy V. Next, we have 3215 phosphorus making 3216 sulfur and a question mark. Notice the atomic mass. The mass stayed the same at 32, but the atomic number went up by 1. That tells us this is beta radiation. And the thing that's missing in our question mark is our beta particle. If you guys have any questions, please feel free to let me know. I know that was a lot. Try not to wait till the last minute to do your homework. Try to do it on the first day that you're assigned it. If you have any questions, let me know. I'm here to help.